This video shows collections being used, and in particular the loop collection operator. Collections are useful because they allow objects to be collected together and treated as one larger object. This makes processes easier to write, debug and maintain. Some operators naturally return collections, and so it's important to be able to confidently handle these to get the best out of RapidMiner. The process shown in this video is a fairly typical cluster validity investigation, which makes extensive use of collections. It shows the loop parameters operator, which returns a collection, and the loop collection operator itself, allowing members of the collection to be processed. So what we'll do is we'll look at a process which does clustering and validity performance measurements. We'll give an overview of that. Then we'll look at the output from the loop parameter operator. We can store collections. Might as well see how that's done. Then we'll look at the loop collection operator itself, inside that to see what it does. Also, there are some techniques to access other collections inside the loop collection operator. And finally, we'll look at the output from the loop collection operator. So, as usual, here's a process. Very simple and at a high level. It generates some data, which we are going to cluster, and what happens is the loop parameters operator tries different values for k to do a k-means clustering, which you can see inside here. The output from that is two things. One is a collection containing each cluster model that's been found, and the second output is an example set, or a collection of example sets with the cluster model applied to them. Then what happens is we actually store one of those in the process's memory, and this here is the loop collection operator, which is going to iterate over each of the various clustering models and work out some cluster validity measurements on them to try and mathematically show which is the quotes best close quotes clustering. That's the whole point of cluster validity measures, is not to actually give the right answer, but to give pointers to what could be the interesting clusterings. So let's first things first, let's look at the data. So I'll set a breakpoint on this generate data operator, and we'll look at it. So it has there are 10,000 examples, 3 attributes and a label, and because 2 cubed is 8, there are 8 possible values of this label. This is what the generate data operator does. If we do some charting, let's do a 3D scatter plot in color. We'll plot at 1, at 2, at 3, and then we'll color it in based on the label. And you can sort of see as I move that around, there are 8 clusters, each colored differently, and they seem to be reasonably well distinguished from one another. So that's good. Next thing is, I'll pause that, go back to the process. Now we're going to go to the loop parameters operator. Now what this does, if I click on the edit parameter settings button, what it's going to do is try all possible combinations for the k parameter to a clustering operator that's actually inside the loop parameters operator. And you can see basically what I'm going to do is try a clustering between 2 and 11 in 10 steps, and you can see in grey here there are k goes from 2, 3 all the way up to 11. What this means is if we go inside here, you can see that we're using k-means to cluster the data, and the value of k will vary between 2 and 11. And the output from that will be a cluster model, which is this top row, and also the example sets with the clustering model applied. What this means is that the loop parameters operator will output 11 cluster models and 11 example sets. And you'll notice that they all go all the way through to the end here. Now here's an interesting point. Why is this performance not connected to anything? In the past, I think this has changed quite recently, it used to be the case you had to provide a performance vector for the loop parameters operator to work properly. It looks like you don't need to do that anymore, which is good. You might ask, what's materialized data doing? Well, this is a gotcha, and it's very difficult to predict, but sometimes if you don't put a materialized data in an example set data flow, things don't work properly. So materializing the data, it causes things, I think, to be flushed properly. If you access the help, you can sort of see from the synopsis it says here, it looks like it's doing some sort of internal flushing to make it all work properly. Anyway, I don't know how it works or why, but I just bitter experience teaches me that it's important sometimes to use this operator to make things work properly. Okay, so let's set a breakpoint at the end of the loop parameters operator. And what this will do, if we can see down here, it's going to iterate 11 times. It's at 6, it's at 7, 8, here we go, 9. And it's finished. Now, if you recollect, there are going to be two main outputs. There's an IO object collection, which is a collection of clustering models. And there's another collection of example sets which have had a cluster applied to them. And basically, you can count them there. There are 11 in this collection. Similarly, 11 in this collection. And basically, this first one will be when k is 2, so there are 2 clusters here. This is 3, 4, and so on, all the way up to 11. And these example sets correspond to what happens if you apply those models to the input data. Okay, so let's go back to the process. So now what will happen is we're going to store, I'm going to call them clustered example sets, and you can store them in the process's context or the process's memory, and you have to give it a type of IO object collection. Okay, so you can store them for later use. We're going to use this later in this loop collection operator. The other thing is we're going to pass to the loop collection operator the cluster models, and we're going to now go inside here and look at what this is going to do. So loop collection, what it does, it automatically loops one time for each member within a collection. In addition, I'm setting a macro which we're going to use inside the operator to access another collection. We'll set that to start at 1. This is optional, by the way, you don't need to do this, but I'm using it for a purpose, you'll see. Unfold, this is a more advanced parameter which I have never used, so I'm sure with a more complex input collection this will become useful. And I guess in a parallel processing environment you could set the parallelized iteration parameter here to get each member of a collection to be processed in parallel. Anyway, we're not doing that today. So what's going to happen is this loop collection operator will iterate 11 times. Let's go inside here. And basically what happens is this data flow here will be one out of the input collection, which in this case were cluster models. So this will come in with a cluster model to this operator here, which is a cluster distance performance operator. That also requires an example set to be passed to it. So this is where we're using the saved clustered example sets, which are here. This IO object collection I saved earlier, and I'm retrieving that from the memory of the process, and I'm using the select operator, which lets you choose one out of a collection, and I'm using the macro, which is the iteration macro, to choose the one I want. So by this method I'm able to pick out matching pairs of example sets within a collection and cluster models within a collection, and I'm passing these to this performance operator here. Now the performance operator is a cluster distance performance. It calculates two things: average within centroid distance and the Davies Boolean measure. I won't go into the details of those, but these are ways of determining mathematically if a clustering is, quotes, good or not mathematically. So what happens is this outputs a performance measurement, and in addition I'm also counting the number of clusters, for the simple reason that I'm using a log operator here to record what the performance measurements were of both the cluster validity measures from this first operator and also the count from the second one. You can see here I'm doing Davies Boolean, average within distance from the performance 2 operator, which is this one here, and also the cluster number from this one. So I'll get a log out which will let me plot a graph of cluster number, and then as a function of that is how does the Davis-Boolean and average within distance validity measures, how do they vary as a function of the number of clusters? Because what we're trying to do is find the best clustering. Okay, so that will iterate 11 times. So let's just run it all the way through. And you'll notice that the output from the loop collection operator, that actually is 2 collections in their own right. And you can see the top one will be a performance vector collection. The bottom one will be a collection of cluster models. Okay, let's run that. So it's going to go all the way through. It's going to do the clustering and then pass the collection of cluster models to the loop collection operator. I've remembered rather the example sets, so they'll be recalled individually. And the output looks like this. So here's the log. First of all, let's look at that. You can see it's recorded the cluster number between 2 and 11, and then various validity measures. If we plot cluster number along the x-axis and Davis-Boolean, for example, along the y, you can see there that let's use series because it shows up a bit better. You can see here that the Davis-Boolean has a minimum at 8. Now, this, in general, what you look for in Davis-Boolean is a minimum. So you can see here 8 is a minimum, and so we happen to know that is the right answer. But you can also see the Davis-Boolean measure gives you a hint that maybe 5 and 6 are also interesting. It obviously knows nothing about the data or how it was generated. You can also look at the average within distance measure, and generally this is harder to interpret, but what you're looking for is a sort of elbow in the characteristic, and there's perhaps one there and sort of one there at 8. So we sort of get the feeling that indeed 8 is a clustering that looks like it could be the correct one. But now we can look at each of these collections to have a look at what they mean. So this first one, this is the performance vector that's output from the loop collection operator for each of the cases between 2 and 11. So this is basically what happened as the average within centroid distance when k is 2. And there's the Davis-Boolean value for that. Here's 3. You can see it actually gives you a low level within cluster distance as well as an average across all of them. And that's 2, 3, 4, 5, 6, 7, 8. So that's the minimum at minus 0.25. In addition to the collection of performance vectors, you also get the cluster models. And you can see this is showing you the various models that were produced. So when k is 8, this is what the 8 clusters were. This is the shape of the 8 clusters, and you can obviously look into that in more detail. And then the final collection is the example sets with the cluster model applied. So here's 2, 3, 4, 5, 6, 7, 8. So this is the k equals 8 case. So if you recollect, if you plot the 3D chart of that, if you remember, this is the labeled data that we knew the answer to already. If we change the color to be cluster, it's done a good job. If let's pick 7, let's see what the picture looks like when it's 7, and you can see it's done a strange thing. It sort of looks like it's picked for some reason those 2 in. Those 2 clusters are in cluster 1. Anyway, who knows why it's done that, but it just has. But interesting to see. You can essentially combine this view of the performance of a validity measure as a function of k, and then you can use these collections to really drill into helping you to understand what happened. Okay, so that concludes that one. What I will do is I will, as a final picture, show the k equals 8 case as here. 3, 4, 5, 6, 7, 8. In fact, for fun, why don't we put 5 up? Because the Davis Boolean measure seemed to think 5 was a good clustering. Oh, maybe that's true. So I'll just leave that here, and you can talk amongst yourselves to decide if that's if it's an interesting validity measure, if it's an interesting clustering.